Links are found in the description box below. A regime shift in the Southeast Greenland marine ecosystem. Abstract. Two major oceanographic changes have recently propagated through several trophic levels in coastal areas of Southeast Greenland, SEG. Firstly, the amount of drift ice exported from the Fram Strait and transported with the East Greenland Current, EGC, has decreased significantly over the past 2 decades, and a main tipping element, summer sea ice, has virtually disappeared since 2003, leading to a regime shift in oceanographic and ecological conditions in the region. The following 20-year period with low or no coastal sea ice is unique in the 200-year history of ice observations in the region, and the regime shift is also obvious in the volume of ice export through the Fram Strait after 2013. In the same period, the temperature of the EGC south of 73.5 N has increased significantly, greater than 2 degrees Celsius, since 1980. Secondly, the warm Erminger Current, which advects warm, saline Atlantic water into the region, has become warmer since 1990. The lack of pack ice in summer together with a warming ocean generated cascading effects on the ecosystem in SEG that are manifested in a changed fish fauna with an influx of boreal species in the south and the subarctic capelin further north. At higher trophic levels there has been an increase in the abundance of several boreal cetaceans, humpback, fin, killer, and pilot whales and dolphins, that are either new to this area or occur in historically large numbers. It is estimated that the new cetacean species in SEG are responsible for an annual predation level of 700,000 tons of fish. In addition, predation on krill species is estimated at greater than 1,500,000 tons, mainly consumed by fin whales. Simultaneously, there has been a reduction in the abundance and catches of narwhals and walruses in SEG, and it is suggested that these species have been impacted by the habitat changes. 1. Introduction. Climate change is affecting the distributions and productivities of species, the interactions among species, and the flows of energy through food webs, IPCC, 2019. Many of these effects have been occurring gradually and/or in proportion to the velocity of climate change. For example, changes in distributions of fish species around North American coasts are strongly linearly correlated with a thermal climate velocity index, Pinsky et al., 2013, and commercial fish catches in regional seas also follow linear changes with local temperatures, Chung et al., 2013. However, changes in species distributions, biodiversity, food web dynamics, and ecosystem functioning can also occur more abruptly in a nonlinear manner. When characteristics of a system, i.e., tipping elements, Lenton et al., 2008, pass beyond critical thresholds, i.e., tipping points, Wassman and Lenton, 2012, the system transitions into a new regime. In the Arctic, tipping elements that are driving changes in marine ecosystems are typically sea ice, sea temperatures and currents, IPCC, 2019. Tipping points are reached when tipping elements exhibit changes that cause abrupt nonlinear changes in the ecosystem, leading to substantial widespread Earth system impacts. Armstrong-McKay et al., 2022. Ecological regime shifts are sudden, and sometimes irreversible, changes in ecosystems that are clearly detectable. They are sometimes driven by underlying environmental conditions, for example, changes in climate systems, Grebmeier et al., 2006, but may also result from anthropogenic perturbations, such as fishing/hunting, eutrophication, or introduction of species, example, Biggs et al., 2009. The new regime will, therefore, have new ecosystem and biodiversity properties substantially different from the pre-tipping point regime. Examples of the nonlinear systems, or tipping point elements, vulnerable to climate change-related tipping point dynamics include the Deepwater Formation and the Atlantic Meridional Ocean Circulation, coral reefs whose survival, structure, and functioning are subject to the effects of acidification and temperature changes, and Arctic sea ice melt and ecosystem functioning, IPCC, 2022. Crossing of the tipping point of these tipping elements represents major changes in biodiversity, ecosystem functioning and the provision of ecosystem goods and services to humanity, and such changes would occur at rates faster than those in the linear dynamic systems associated with recent climate change velocity estimates. Here we hypothesize that the large-scale marine ecosystem adjacent to Southeast Greenland, hereafter referred to as SEG, see Figure S1, has already crossed such a tipping point in the past 1 to 2 decades and has entered a new regime. We investigated changes in the climate, physical oceanography, megafauna community, marine mammals and some key fish species in the food web, and some trophic interactions in the Southeast Greenland coastal and shelf ecosystem since the early 2000s and compared them with historical data. Hydrographically, the coastal and shelf area of SEG has usually been covered by dense masses of multi-year drifting pack ice originating from the Arctic Ocean and transported southward by the East Greenland Current (EGC) through the Fram Strait along the coast of East Greenland. Figure 1, Schmith and Hansen, 2003. Because of the regular and seasonally extensive ice cover in the region, the marine mammal community includes several ice-dependent species tolerant of cold temperatures. These include narwhals, Monodon monoceros, walruses, Odobenus rosmarus, hooded, Cystophora cristata, and ringed seals, Pusa hispida. The fish community has been mainly composed of demersal, bathopelagic, mesopelagic and ice-adapted species, example, Greenland halibut, Rheanhardtius hippoglossoides, redfish, Sebacetes sp., polar cod, Boreogodus sida, Asthorson, 2016, Muller et al., 2010, typical of boreal polar ecosystems, Van Denderen et al., 2018. Continues.